Koichi, could you introduce Kengo?
Yes. Today we are introducing Dr. Kengo Tomida from Princeton University. He will talk about Athena adaptive image refinement framework. So please go ahead, Kengo.
Okay, so can you hear me? And can you see my screen?
Yes, we can see your screen and we can hear you well.
Okay, that's good. Let me stop my camera to save some videos. And okay, so let's begin. So thank you very much for the invitation, and thank you for joining the seminar, because I thought it was the time for summer vacation, but then I got so many participants and I'm quite happy. Okay, so let me start. So today I'm going to talk about the Athena++ adaptive image refinement framework. That's a new code we have developed. To start with, let me introduce myself. My name is Kengo Tomida, and I am an associate professor at the Tohoku University. And I have two major streams of research. One is the development of Athena++, which is a public image simulation code in collaboration with Jim Stone and other people, mainly in the US and other countries worldwide. And this is a versatile, robust, and fast image simulation code. And not only developing it, but I support it, and also I held some summer and winter schools worldwide. So this is today's main topic. But scientifically, I have been working on star formation and disk formation using realistic radiation image simulations. So I started from the collapse of molecular clouds until the star and the surrounding circumstellar disks are formed. And also I have performed some synthetic observations to simulate how it should be observed and compared it with real observations, particularly in this ALMA. So let me show some examples of my star formation research. The right panel is the simulation movie of the non-ideal MHD simulations, including radiation transfer. This includes both an ohmic dissipation and bipolar diffusion. And previously, it was thought that the disk formation is difficult in early phase of star formation because the magnetic fields transport angular momentum very quickly, which is called the magnetic braking catastrophe. But in this simulation, we have shown that the bipolar diffusion and ohmic dissipation remove the magnetic flux from this disk scale and suppress the angular momentum transport by magnetic fields. And as a result, this circumstellar disk is formed. And in this simulation, the disk is still small. It's only a few AUs in radius, but it is actually very massive, and it's actually comparable to the central star, and the disk becomes gravitationally unstable, and as a result, these spiral arms are formed like this. So it's wobbling, and this is an indication of spiral arms. And this is very short-term simulation, so I extended it using a so-called sync particle technique, and had run a very long-term simulation until the end of the class 1 phase, so until almost all the accretion from the envelope completes. And I applied the synthetic observation technique, and here these are results of the observation simulations. So the left panel is a synthetic observation based on the MHD simulation, and the right panel here is the actual observation of Elias 227. And this object has two beautifully symmetric ground design spiral arms, and at least qualitatively, we could reproduce these two symmetric spiral arms. So in our simulations, these spiral arms are due to the gravitational instability, so it's thermal instability. So from this direct comparison with synthetic observation and actual observation, we concluded, we suggested that these spiral arms are actually formed by the computational instability, and this circumstellar disk is actually massive. So this indicates that actually there is plenty of mass in the disk, so star formation can, planet formation can already start in the early phase of star formation. So that's my star formation research, but then I stop here about it. So if you have any question about my star formation research, then you can talk offline. Oh, by the way, I'm happy to take any question during the talk. So if you got a question, please feel free to stop me at any time by raising the hand on this one. Yeah. All right. So let me proceed. So let's move on to Athena++. So Athena++ is a new public image simulation code for astrophysics, and this is a successor of the Athena public image code. So let me give you some historic background. So Athena was Jim Stone and his collaborators' third code, which is published in 2008. And he had three codes before that, including Athena, he had three codes before. So the first one is renowned Zeus code, and I know some of you guys are using it. And the second one is a little known smart code. And from his experience, he thought that an simulation code has lifetime, and which should be about 10 to 15 years, because computers advance and the best simulation code design changes as time goes. So we think Athena was successful. It was considered as the most reliable code in the field, but there are already several problems as it was getting old. For example, the code was poorly maintained, and honestly speaking, some parts were broken, and the maintainer left the field, so we couldn't fix it. Also, this is probably the biggest problem, but it was not optimized for the modern architecture. And so when Athena was initially developed, the concept of vectorization or simile were not very important at that time. But today, to get the maximum performance out of modern computers, it is necessary to vectorize or apply the simile concept to the code. Also, the original Athena was not flexible enough, and it didn't support, for example, flexible coordinates like curvilinear coordinates, and also adaptive mesh refinement wasn't supported at that time. And Athena did not support some key features in Zeus, including spherical and cylindrical coordinates. So some people couldn't move to Athena from Zeus. So that was a big mistake, I think. So we decided that it is time to redesign the next generation code from scratch. So that's the beginning of the Athena++ project. So when we started this new project, and we set up the design policy. And first, so we decided to use mostly the same basic, well-established algorithms which is used in Athena. That is, for example, for MXT, the finite volume method using the Riemann solvers, approximate Riemann solvers, like Rho or HLD solvers, and constraint transport for magnetic fields. That's a very established design and well tested and well trusted in the field. And the important point is to optimize the code and data structure for modern architectures. So we completely redesigned the parallelization and also the data structure. So in old Athena, the data is stored as a so-called arrays of structure. But now we switch it to structured arrays to enable efficient vectorization and cache vectorization. Also, we introduced a new communication pattern for beta parallelization. Also, because today, the adaptive mesh refinement, which I will discuss more in detail later, is one of the key ingredients in the modern astrophysical simulation code. we designed the code from the beginning that adaptive mesh refinement in mind. But at the same time, we didn't want to optimize the code too much to specific machines. So we avoided machine-specific optimization. And also, we do not want to sacrifice the readability. So we didn't go to very, very aggressive optimization, including using some assemblers or intrinsics, which depends on specific machines or architectures. But it turned out, as long as we have reasonably good compilers, our design works reasonably well, and we can get quite good performance in many architectures. I can show you the results later. Also, we want to support various physics and coordinate systems used in astrophysics. So from the beginning, we designed it with an MR and general relativity in mind. Also, what is very new in Athena++ is a new design called taskless. I'll discuss this later. And we want to keep this code sustainable. So also, we want to make it reliable, easy to use, and easy to maintain. And we do not want to follow the same path as Athena took. So we want to support it for long term. So we prepared a comprehensive documentation and tutorial website so that everyone can learn it online for himself or herself. Also, we minimize dependency on external libraries. So Athena++ only requires MPI library, and optionally it uses HDF5 library for output, but then HDF5 is also not required. So practically, you can learn Athena++ on practically any computer. Okay, and also we wanted to enforce a strict quality control. So we verify the code consistency through extensive tests. Every time we upload the code, it has to pass all the test programs we have set. Okay. So you can download the code from this website, athena.astro.app, and also you can find the wiki documentation like this. So if you are interested, please go to this website and try it. And now this is a big international collaboration. So we have many contributors worldwide. So mainly it is developed in Princeton Institute for Advanced Study and Princeton University, like Jimson, Eagles Writer, and their postdocs, but also in Japan, including myself and Iwasa-san at NLJ, and Tanaka-san is actually now in the US. Yeah, so there are many, many contributors in the world, and we are so excited to have this team. Okay. Yes. Question? Go ahead.
Yeah, I just wanted to ask, in your adaptive mesh framework, what type of space filling curve are you using, and what is the reason for choosing that particular type of space filling curve?
Okay, so I have a slide for that, so please wait for a moment. Okay, I'll come back to your point quite soon in a few slides. Okay, so let me continue. So currently in Athena++, the public version supports these many features. So it's an MHD and also flexible coordinates and static and adaptive mesh refinement. So general relativity and special relativities, polarization, passive scalars, self-gravity, sharing box and orbital direction, resistivity, general US. So actually, it is already quite versatile, so it has a potentially it has the potential to be applied to your application. If you are interested, please take a look. And there are some features which are already developed but not released in the public version, including the Hall effect, radiation transfer following using software to direct transfer or ray tracing. This is only for this is an explicit implementation, so this is only for high energy systems. It can be useful for some programs. It is not very useful for star formation because for star formation we need radiation transfer in implicit because the time scale is so different. But still, this is applicable to, for example, to black hole acquisitions. We also have a chemical reaction modules, which is developed in Germany, but it is not released yet. And also, the full general relativity is actually developed by the Suda et al. And this will be merged into the main Athena++ at some point, but not yet. We are also developing particle modules and also cosmology extension, hybrid peak plasma simulation, and now actually Jim Stone and colleagues at IAS are developing the new version supporting GPU. So this is actually a separate branch from the main Athena, Athena++. So let me see. Let's say. So it is actually, it starts from a simpler version, so it supports less physics, but then it supports GPU and also other architectures. So it is actually already kind of public on GitLab. So if you are interested, also you can take a look at this project. And in the future, we are planning to introduce more physics like radiation transfer using the implicit integrator, Amphora diffusion. Amphora diffusion is already included in this diffusion model, but it's on a single Fourier approximation. But for some realistic programs, we need two Fourier approximations, so that's on the plan. Also, for synthetic observation, we want to introduce post-processing radiation transfer. And this heterogeneous polarization is a kind of new concept. So this means that on some computing nodes, we calculate, for example, hydrodynamics, and on other nodes, we calculate, for example, gravity. And this enables more flexible load balancing and better performance on the very massive parallel computation. That's just an idea that we are setting of it. Okay. All right, so let's come back to the AMR. So first of all, let me discuss why AMR is so important in astrophysics. So let's take an example of star formation. So suppose the sun is a sphere of 1 meter in radius. So then the scale of the Earth's orbit, 1 AU, is about 200 meters. So this is like from my office to cafeteria distance. And then the size of the solar system is about 35 kilometers. So that is like from ASIAA to the Taoyuan, sorry, I cannot pronounce it right, but Taoyuan airport. And also the size of the molecular cloud of 4, which is the initial condition of star formation, is order of 0.1 parsec. So then this is like about 5,000 kilometers. So that's like the size of the whole US from the East Coast to the West Coast. So the star formation process involves the scale change of the dynamic range of like identifying one person in the US. So using the uniform grid, this is impossible. You need like millions times million cells, which is impossible even using the best supercomputer available in the field. So for this kind of program, AMR is necessary. Okay. So as someone asked the question, so there are actually different types of adaptive mesh refinement designs. So let me explain that. So the first one is this what I call block-based. Some people call this arc-based, but let me call this block-based. So in this case, we can place rectangular blocks in the simulation grid, So to resolve this ellipsoid, so that we can cover this ellipsoid with this rectangular hybrids of higher resolutions. And this design was the first original design of AMR proposed by Berger and Colera 1989. And therefore it was popular and it was adopted by many codes like Enzo, Pluto Chombo library, and Castor and Box library. And also the old Athena had this design's static mesh requirement. And the benefit or advantage of this implementation is it is efficient because it is essentially uniform grid within each block. So we can use existing scheme within each block. But the disadvantage of this design is that this grid placement or arrangement are not unique, and you need some calculations. Also, this grid generation is non-trivial, and even worse, it is hard to parallelize because the load balancing is very complicated. Also, the communication pattern with the neighbor is non-trivial. For example, this one block has many neighbors. So you have to calculate how to communicate each time step whenever the grid is redefined, regenerated, or destroyed. Okay, and the second option is this what I call opt-tree block-based AMR. So in this one, we actually split the whole domain into the same size or same shapes of blocks. And whenever we define the block, actually we just split one block into 2 by 2 or in 2D or 2 by 2 by 2 in 3D, smaller mesh blocks. So then, in this design of adaptive mesh refinement, the benefit is again, this is high efficiency. So within each mesh block, the design is, we can use the same existing scheme because it's just an uniform grid. But the advantage compared to the first design is that the communication pattern is much simpler because every time we define the relation to the lower level or higher level is either it faces on 1 or 2 final or same level or fourth level blocks. So the communication is much easier, and the parallelization is straightforward. Just we can use the so-called space filling part to calculate the load balancing. So that's very efficient and easy, actually easy to implement. And the disadvantage of this implementation is actually already graphically indicated. So it doesn't fit the solution very strictly because the location you can define is limited. Because we always need to refine the parent block into the 2 by 2 or 2 by 2 by 2 child blocks. Okay, so in that sense, this requires more memory and requires a little bit more computation. But we believe that we can actually compensate the loss due to this inefficient grid generation by performance of this from the simple design. So ASIAA++ adopted this design, and this is also used in some other codes like Flash or Paramesh library, and there are other AMR codes like Piano, Nirvana, Supermark. And to answer the question someone asked, we use so-called Morton ordering or Z ordering for the space filling curve, and that's actually the cheapest space filling curve, and it is not it doesn't return a very compact distribution of blocks compared to, for example, the piano-Hilbert curve. But then this Z ordering is cheapest. Actually, we can calculate without any complicated calculation. Okay, go ahead. Something?
Yeah. So you are using Morton-based SHC for a block structure grid, right? But I'm just curious. Don't you think you, since you are not, since you are strictly focusing on a structured formulation, don't you think your classic piano invert or just invert SHC would be more efficient for your neighbor finding algorithms? Because Morton will not give you a proper, I mean, Morton numbering is very random, right? You don't have a, I mean, you need to go for a neighbor search after you once your tree is formed. But
So,
if you,
you are right. At least theoretically, the Morton ordering is not very good, and it is not very localized. So your physical neighbor can be located logically very far away. So in that sense, this is not optimal space filling curve in that sense. However, we are using it just for polarization, and at least empirically, we found that I will show you the result later, but our implementation is scalable enough. So that means that the communication cost is actually low enough compared to the computation. So at this moment, we concluded that the Morton order is fine, and the gain actually the communication part only costs like 10% of the whole computation. So that means that improving the communication part doesn't help very much. So that's why we, let's say, I can't say it is compromised, but it is good enough, at least for the moment. However, in the future, for example, if we go to more communication intensive physics, or if we have to go to say medium processes or even more, so then we may need to think about it. But at the moment, at least empirically, we found this is good enough.
I think, thanks.
Yep. Okay. And the last option of AMR is this cell-based AMR. This is a kind of extreme of the extreme of this oct-3 block based. So you can actually split each cell into the smaller cells. So this fits to the solution very well. Actually, this is in that sense optimal, and it is mathematically beautiful. However, the problem is that this implementation is not very computationally efficient because first, you always have to search on the space filling curve to calculate which cell your neighbor cell exists on the memory. And this prevents an efficient computation because it doesn't vectorize or simulate very well. And the problem is that the code is hard to write, hard to read, and even worse, it is hard to analyze the results. There are some examples of the code using this design, like Ramses code and R code in the field. But then, based on these considerations, we decided to adopt this design piece of 3 block based ML. And in C++, we split the logical grid and physical coordinates. So our AMR supports any coordinate system as long as the foundation and restriction operations are provided. So from the beginning, we could support, for example, curvilinear coordinates AMR. So this is an example provided by Jahan Zhu at the University of Nevada. So this is an kind of demonstration of a circumplanetary disk embedded in a circumsphere disk. So here, this top left panel shows the whole computation domain. So that's an planetarities rotating around the sun or processor. And here, there's a planet which is launching spiral arms. But as we zoom in to this planet, there's actually certain planetarities with these spiral arms. And we can zoom in to this planet, and we can actually resolve the very detailed structure of the accretion disk onto the planet. So this is one example of the our adaptive refinement in curvilinear coordinates. Okay, and another peculiar and characteristic feature of Athena++ is the dynamic scheduling with the task list. So in most of the simulation codes, usually we fix the ordering of computation when we program the code. So like first we calculate the fluxes between the cells, and then we transfer these fluxes to the neighbor nodes, and so we this is communication. And then we have to wait for this communication message arrival, and then we update the hydrodynamic values using these fluxes, like that. However, if we fix this ordering, we lose some chances of optimization. For example, sometimes we don't have to wait some communications, and some tasks are independent from other tasks. So we can actually, instead of waiting the communication, we can actually already do some computations. But sometimes it is very difficult to predict the behavior in advance. So we change the mind. So in Athena++, we adopted this task list design so that the code can automatically change the ordering of tasks and maximize the potential to overlap the communication and the computation. So let me explain. So in this design, we split computation into small tasks and put them in the task list. So this is a so-called waiting queue and with some dependencies. So each task has a dependency, and we just put these tasks in the task list queue, and the code processes this task list from the beginning. So this figure explains the example. So let's say this mesh block A is on process 1, and this mesh block B is on process 2, and these are parallel calculations. So on mesh block A, first we run this work 1, and then we want to send the result to the neighbor. So that's this send task. And this send task has a dependency on the first task, this task ID 0001. It's set here as a dependency flag in this second task. So when this send task is executed, the code checks the dependency flag. So in this case, the first work 1 task is already completed, so this dependency is cleared, so we can process this send task. So then we proceed to the next receive task here. And this receive task also depends on this first work 1 task, 00001. But it is already cleared, so we can do this. However, sometimes this receive task has to wait this mesh block B, the data from the mesh block B arrives to mesh block A. But sometimes it doesn't arrive yet. So then, usually we have to wait here. But in our code, the code actually goes to the next task, this work 2 task. And this work 2 task has a dependency flag of 00001. So this means that it doesn't depend on this receiving task. It only depends on this work one, which is already clear. So we can actually execute this work two already. So then we can overlap this communication and the computation work too. So then we can minimize the waiting time and maximize the computation efficiency. And then I wrote this work 3 has a dependency flag of 0, 1, 1, 0, 0, which means that this depends on 0, 1, 0, 0, 0 task, so work 2, and also 0, 0, 1, 0, 0 task, which is this receive task. So this work 3 has to wait until this receive and work 2 are both completed. So this dependency flag guarantees that the correct ordering of the computations. Okay. So by this design, we can actually improve the modularity of the program. So because once we split the tasks, its implementation and the dependency, we can actually implement them separately. So we can assume that within each task, we can assume that all the dependencies are already clear. These dependencies are handled by this task list controller. So the code becomes much more modular and easier to maintain. That's a big advantage of this design. And also, as I discussed already, this maximizes the computation overlap. So this has an advantage in performance of the. Okay, so this is a new feature of Athena++. Okay, so let me show some examples of Athena++ calculation. So this is just funny demonstration of the code. So this is an Athena++ logo which is blasted away by a shockwave ejected from the center. And these Athena++ characters are written using so-called cooling function. And this shock is launched from the center. And then we applied adaptive mesh refinement. So this code, this simulation demonstrates that an Athena++ can support adaptive mesh refinement in Pavilion linear coordinates. But at the same time, actually, to implement this simulation, you don't have to change the code itself. You can actually implement this simulation just using the provided user interface. So this demonstrates how flexible Athena++ is. All right. Yes. So then go ahead.
Yeah. Sir, in your linear coordinate, because you are still going for your finite volume method, right? So in your linear coordinate, how are you defining the cells in front?
Okay. Yeah. So in finite volume method, so the center has to be defined consistently, and it is actually volume average center. So it is not arithmetic center. So for example, let's say x left plus x left is on the left side and x r is on the right side. So the center is not half of x left plus x right. It's an integration of x with appropriate weighting.
Yeah, so the cell center will be calculated automatically, or the user have to define when he is implementing a new coordinate system?
Yes, you have to provide a function to calculate it. But that is already, at least it is already implemented for spherical, polar, and cylindrical coordinates. So you can just copy and mimic the implementations.
Thanks.
Yeah. Any other questions so far? Okay, let me continue. Yeah, I'm afraid I'm speaking too much, so let me go quickly. So another demonstration of this code is this 3D blast wave and the comparison with the self-Taylor solution. So here this is pointless simulation, but to demonstrate our capability, we injected this blast wave in spherical polar coordinate. And you may think that this blast wave is warped, but it's not. Actually, here this is a circle, and as you see, it is almost perfect sphere like this. And the right panel shows the comparison between the analytics self-Taylor solution and the result from adaptive mesh refinement. And the top is Cartesian, and the bottom is spherical polar coordinates. And as you see, ASIAA++ can reproduce the self-Taylor solution quite well, even in spherical polar coordinates with adaptive mesh refinement. So that's a demonstration. And I think the most important thing is the performance. So the left panel is a comparison with other cores. And this is a weak scaling test. So that means that when we change the number of processes or number of computers, we keep the size of the program per process or per core. And it is 64 cubic cells per core. And this is ideal MHD. So as you see here, the Athena++ is this on the top upper line, which is almost perfectly flat up to the about 5,000 cores. And the other cores, so this yellow line is Pluto, and this green line is old Athena, and the blue line is Enzo, and this orange line is Flash. So so as you see, Athena++ has the best performance among them. But it's not only about the performance, but what is important is the scalability. So at the massively parallel region here, all the other cores start to decline because of the communication cost. And if you know the Amdahl's law, if it starts to decline, actually it declines very quickly. However, Athena++ still maintains almost perfect scaling here. So the question is, how far can we go? So we run Athena++ on the Fugaku supercomputer in Japan, which was the world's largest machine until last year, but then now it's second or third, whatever it is. So here, this purple line is traditional NPI implementation, but then Fugaku has its own special network interface. So I implemented new communication modules using it. So it has better performance here. And as you see here, we can achieve like 92% with more than 500,000 threads on Fugaku. So that is actually quite good. So far, as far as I know, no other code can do that. So so here, as I showed, it is faster than other public codes, other astrophysical AMR MHD codes like Enzo and Pluto and Flash. And as you know, Enzo and Flash are almost national projects of the US. They have both big centers and hired many people. But Athena++ hired only a few postdocs and students. But we can do better than those $1 billion projects as long as we do it right. And so I'd say Athena++ is ready for the exascale era. And this is the scaling of the AMR part, but I'm running out of time, so let me skip this. And this is also this is about the design of the gravity server, which I'm now working on. So traditionally, previously we used an fast Fourier transform to solve the self-gravity and Poisson equation, but the FFT is not compatible with adaptive mesh refinement. And also FFT, sorry, previous we used an fast Fourier transform to solve the self-gravity and Poisson equation, but the FFT is not compatible with adaptive mesh refinement. And also, FFT, it's not compatible with adaptive mesh refinement. And also, FFT, it's not compatible with adaptive mesh refinement. And also, FFT, uh, is not compatible or how to say, it's not trivial to apply arbitrary boundary conditions. And FFT is compatible with periodic boundary conditions, but for other boundary conditions, we need to tweak the code. So we need more flexible and efficient servers. So we decided to implement a new server based on the so-called multi-grid method. But let me skip the detailed discussion. If you are interested, you can ask me later. So this new Python server based on the multi-grid method is already almost completed and it's now being tested. So this is the performance. This left panel is the performance. So the horizontal axis number of processes, and there are many lines, but these are using different number of cells per mesh flow. And this red line is the MHD performance. So let's compare in the same setup. So this cyan or blue line is the same size of mesh flow. So this line. So as you see here, the vertical axis is performance in the unit of cells per second per process. So compared to this MHD part, the self-gravity is like 5 to 8 times faster than MHD. And so it starts to decline earlier because multi-grid, even with multi-grid, the person server requires global communication. So at some point, we have to deal with the communication cost. So it doesn't scale very well compared to the MHD, but still it scales reasonably well up to say 600 cores. So now you can actually introduce self-gravity only say a factor of 2 cost even with 10,000 processes. And also let me note that this black line is the performance of the self-gravity server using FFT. And FFT doesn't scale very well, so it declines from the beginning continuously, and it is not as fast as MHD, even at around 1,000 cores. And there is nothing wrong with FFT itself, but FFT's cost is order of n log n, while multi-grid and MHD are both order n. So people say that this log n factor is small, but it's not. Actually, it becomes visible quite quickly, at least using today's supercomputers. So we can say that this new multi-grid server is superior to the FFT server. And now this is almost completed, and also it is compatible with adaptive mesh refinement like this on the right. So it is already uploaded on the GitHub. So if you are interested, you can try it right now, although it's still in the beta test phase. Okay. All right. So that's about it, about the code design. So let me show you some scientific applications. But do you have any questions at this moment?
Well, Kengo, it might be best for you to finish the presentation, then we can save the questions near the end.
All right. Okay. So let me go quickly about the science applications. So using this code, we are doing some star formation and planetary simulation. So let me show you some examples. So this is an molecular cloud formation simulation. So it is known that molecular clouds are formed in strong compression and in the galaxies, like supernova shocks or galactic spiral. So we simulate such a strong compression using this converging flow setup. And in these simulations, we compare the effect of the magnetic field. So in the left panel, the magnetic fields are spreading almost horizontally. So theta equals 0 degrees, that means it's completely horizontal. And on the right panel, it is slightly tilted to 11 degrees. So it's actually only slight tilt. But as you see, this makes a drastic difference in the outcome. So in the left panel, these dense clamps actually go through each other because the magnetic fields prevent perpendicular motion. But on the other hand, on the right panel, these magnetic fields are actually compressed by this compression flow, converging flow, and it drives this kind of turbulent flow in the post-shock region. So we found that there is a sweet spot of this compression ratio, or we would say this is formation efficiency of the molecular cloud. So if it is the magnetic field lines are parallel to the converging flow direction, it doesn't compress very well. But at some point, there's a kind of critical angle here, and it is about a few, like 10 degrees. Then we can get maximum efficiency. And then it starts to decline because the magnetic pressure in the post-shock region gets higher and higher and prevents the strong compression here. So this indicates how magnetic fields affect the formation of stars and molecular clouds. And these are just 3D representations of the magnetic fields, like this. And now, because we already have a self-gravity solver, we run, so this calculation was without self-gravity, but now we introduce the self-gravity here and see what happens. So without self-gravity, this converging flow produces these structures. These are current density map shown along the line of sight parallel to the converging flow direction. So, so without gravity, actually the density enhancement is not so strong. But with gravity, strong compression can happen. And in the left panel, where the degree of angle between the field lines and converging flow direction is small, it produces these core-like structures. But if it is tilted like 11 degrees, then the gas is compressed along the magnetic field lines. So the elementary structures perpendicular to the field lines are formed by the self-gravity here. So it is obvious that self-gravity is a key ingredient in the core and filament structure formation. So then, from this simulation, we can extract the properties of the molecular cloud pores formed in this converging flow simulation. So this is published in our latest paper, Iwasaki and Tomida 2012-22. So we found that the Villiers parameters, that is a ratio of the kinetic, magnetic, and total energy versus the gravitational energy, are actually following the universal scaling relations like this. So here, these red, green lines and dots indicate different plots for molecular cloud pores with different threshold densities. So red means that the threshold density is 10 to 3.5 fifths, and the green is 10 to 4th, and blue is 10 to 4.5. And these, these top panels and bottom panels are from different models. But as you see, these curves, these molecular cloud pores actually follow the same curve regardless of the simulation setup. So we can say that the molecular cloud pores forming in these converging flows follow the universal scaling relation. And also the right panel is the comparison of the density versus the magnetic flux in different simulations, not only our work, which is indicated by green, but with other group simulations. And we found that actually, at least in the high density region, they all converge to the same B versus N relation. So this means that the star forming clouds actually follow a kind of universal scaling relations. So then this can be the origin of the universality of the star motion processes. For example, the universality in the initial mass function. Possibly. Yeah. And now we are using this simulation result for synthetic observation. So because we have magnetic fields, we can actually measure the polarization signal from this molecular cloud formation simulation. So then we can compare it with, we know the actual magnetic field in the simulation. So then we can actually do synthetic observation and apply, for example, the Chandrasekhar-Fermi method, which is used to measure the magnetic field strength from the observed polarization pattern. So then we can compare these results and we can discuss how accurate this observational method is. So then we found that yes, and they are reasonably accurate but not perfect. So we found that so this horizontal axis is the total versus the sky, and the vertical axis is the ratio between the magnetic field strength inferred by the Chandrasekhar-Fermi formula versus actual B plane of sky. So then it remains around, say, 0.5. So this means that the Chandrasekhar-Fermi method or its variation like centralized velocity method by Cho and Liu are somewhat biased, and it misses about 50% of the actual magnetic field. So we can discuss the actual magnetic fields in comparison with simulation and observation. Let me skip this. This is an protoplanetary disk simulation. The vortex is produced by Rossby instability, but let me skip it. So the last thing is a protoplanetary disk. So I am interested in star formation, but to understand the star formation, we want to understand how the gas accretes through the protoplanetary disk onto the protostar, and also we want to understand what is the initial and boundary conditions for planet formation. So we are running on a very high resolution global 3D no-ideal MHD simulations, including ohmic dissipation and bipolar diffusion. And with a focus on this dead zone boundary. So what happens where this resistivity changes? So then, as you see here, in the inner region, the gas is highly ionized. So this the gas is almost ideal. So then MRI turbulence drives the disk accretion, and also from the disk surface it drives the wind pushed by this turbulent pressure. But then as we go outside, where this blue region is dead by bipolar diffusion, and this red region is dead by ohmic dissipation. And as you see here, in this dead regions, this is more or less laminar. And in this case, in the mid plane, the accretion doesn't happen so strongly because it is dead and magnetic stress is not very strong. However, near the surface, the gas still can accrete because the surface layer is still coupled, and the large-scale magnetic fields can actually transport the angular momentum. And then on the right panel, we plot. Sorry, I forgot the ladder, but this is a column density and normalized by the initial column density. So the bright region gets a higher density compared to the initial condition, and the dark region gets lower density compared to the initial condition. And initially, because of this turbulence, the gas in the central region is reduced. It accretes onto the protostar, but as we see, there are rings and gap structures being formed. You can see here, and this blue line is the boundary of the ambipolar diffusion dead zone. So we found that the gas accumulates around this ambipolar diffusion dead zone boundary here, and it takes regional. So just let me skip like this. So eventually it forms this ring and gap structures, and this we are interested in how these structures affect subsequent planet formation processes. However, I have to emphasize that this is actually very small scale phenomenon. So this radius is less than 1 AU because this is so-called inner dead zone region. So in a dead zone boundary. So this is completely different from the scale observed in, for example, the HL palm or TW hydra disks. However, it is interesting that such structure formation is possible by the non-angular energy effect. And also we are studying how magnetic flux is transported in such a disk because this magnetic flux transport is important in the context of the stellar magnetic flux. Also the structure and the evolution of the planetary disks. So we found that the magnetic flux can be transported quite fast. Actually, the magnetic flux can be transported at the speed of a few Kepler velocity. So that means that in a field rotation, the magnetic fluxes can move significantly. However, what we found is that the direction of this transport actually depends on the dust properties. So here on the left panel, we set the dust to gas ratio is 10 to minus 4, assuming that this disk is already evolved and the dust are significantly depleted. So then the magnetic flux is transported outward. However, on the right-hand side, using the fiducial dust to gas ratio in the ISN, actually the magnetic flux is transported inward. So these are very interesting and can have a significant impact on, for example, how much magnetic flux a star can acquire during the accretion phase. But we are still investigating this process in detail. Okay, so this is still preliminary, but please stay tuned. And the last thing I want to show is the star-disk interaction. So this is even the smaller scale simulation. So at the innermost region of the accretion protoplanetary disk, the gas in the protoplanetary disk accretes onto the star. But if the stellar magnetic fields are weak, so then the disk can directly accrete onto the star by the turbulent viscosity produced by MRI. But if the stellar magnetic fields are very strong, so then stellar magnetic fields will truncate the disk and will produce a strong so-called magnetosphere, and the magnetospheric accretion from onto the polar region will be realized. However, in the left simulation, we simulated an accretion disk with a very big magnetic field of the star, but we still found that this strong accretion flow onto the polar region. And this is due to the failed wind. So some gas is lifted from the disk by MRI as a wind, but they lose angular momentum by the magnetic field in this ambient gas. And then it falls down onto the polar region. So we found that the accretion onto the polar region does not necessarily mean that there is a strong magnetosphere, and the failed wind can produce similar signatures or structures like this polar region accretion. So that's a new finding. This is in Takasao 2008. And another thing is that we are also running a non-ideal MHD simulation to simulate flares from the young protostars. So it is known that young protostars are bright and has a strong variability in X-rays. And these are considered as flares by these protostars, but protostellar flares are actually much larger than the solar flares. It's larger by, say, 5 orders of magnitude or even more. So it is not trivial. How can a protostar produce such a large energy? Because to produce such a large flare, we need a very large energy reservoir to produce such a high energy emission. So in this simulation, we found that a big reconnection can produce a strong flare, and this reconnection happens not on the surface of the star, but it happens as an interaction between this stellar magnetic field and this magnetic field. So such a flare can explain the observed giant flares observed in X-rays. And this is a movie, but yeah. So here, this is showing the high temperature. This volume rendering shows the temperature, and here the reconnection occurs, and this is a high energy outburst occurs here, and it ejects these hot plasmas partially. Yeah. All right. So these are examples of an Athena plus simulations. So let me summarize. So we are still developing new features like an post-processing radiation transfer and also another implicit radiation transfer with multigrid, particle modules, cosmology, and bipolar diffusion. Also GPU support using Cocos library and full general relativity and so on. So we expect further international collaboration through this code development. So this is a summary. So ASIAA++ is a new multiphysics MHD code for astrophysics. So it already has many physical processes like gravity MHD, non-ideal MHD, general universal radiation transfer, relativities, particles, and so on. So you can already apply it to your program. So if you are interested, please try it and feel free to contact me. And last thing is that let me advertise a big conference next year that's Protostar Planet 7. So this is the biggest conference, international conference on star formation and planet formation. And it will be in Kyoto International Conference Center from April 10th to April 15th next year. And the registration is already open, and the review chapters are already uploaded, so you can read and make comments on it. So please register to this conference if you are interested. Okay, thank you. That's it. Sorry, and I speak too much, but yeah, that's it.
Thank you very much, Kengo. Are there any questions or comments? Well, I have a comment. Thank you for your exciting talk. I really enjoyed. And if you incorporate general relativity and apply it to black hole magnetosphere, then you can apply it to radio loud craters. Because low density AGM such as M87 for such low density AGMs, we cannot directly apply energy code. Instead, we may have to apply, for instance, two fluid model or particle inside simulations. However, for radio land craters, I consider that energy approximation holds well, and we can directly apply the code to such highly accurate systems.
Okay, yeah, thank you for the suggestion. Yes, and I think that's possible, and I think Shane Davis in Virginia are interested in such an application, and he's also developing a radiation transfer module to calculate, for example, spectrum from such an black hole accretion disk. So yes, and yes, that is a good application for the code. Yeah, thank you for your suggestion.
It's a pleasure. Well, for question disks, to apply standard NHD code, I think we can apply only to standard Shackleton's net for null type, not to abstraction related accretion for. So in such well, in such medium as well, you can, I think, apply to highly aggregating system that have standard accretion disks.
Okay, yes, yes. Yeah, personally, I'm not a black hole person, but yes, and I think there are many users already interested in it and working on it, I think.
Thank you very much. And enjoy your excellent talk.
Good. Okay.
Any other questions?
Kengo, I'm wondering about your task list. Any ordinary user need to know how to fix the task list, or it has to be only fixed at priority by the developers or other people when other users can they do their own task list?
All right. So usually users don't have to be aware of it. Basically, it's the code which creates a task list. So, but when you develop a new module, new physics, so then you have to understand where you want to put your new module in this task list. So yes, it's for developers. And the users don't have to know that or don't have to worry about that.
Right, but any experienced user developers can fix their own task list, right? Correct? For their own new models for implementation.
Right. Yes, they can.
Any other questions?
Tomida, I have a question here.
Yeah.
It's a small question. It's regarding your post-processing radiation transfer. Is it based on Monte Carlo or some other techniques?
So yeah, it's still actually planned. So we have different versions, and but basically yes, and the idea is that using the Monte Carlo to calculate, for example, the temperature distribution or the excitation level applications, and then apply just a 1D ray tracing to calculate, for example, the map, intensity map or spectrum.
Okay.
That's quite standard procedure, like for example, Protein C does. Right? Yeah.
So in your OpenMP implementation, are you OpenMP parallelizing per block or per task?
Okay, so that's a good question. So usually people apply OpenP for each loop, right? For example, if you are calculating hydrodynamics, and so to calculate the fluxes, and if you have usually you have triple loop like Z, Y, X, and you just apply OpenP for this outermost Z loop. But it doesn't scale very well. It's slow because OpenP threading, launching threads and synchronizing threads cost actually very, very badly. So we apply OpenP threading for each mesh block. So in Athena++, mesh block is a unit of parallelization for MPI. So each MPI process owns one or more mesh blocks. but at the same time, we applied the same parameterization for OpenP. So once OpenP thread is created, it keeps that mesh code from the beginning to the end, and it behaves. So OpenP thread is essentially same as MPI process. So by doing this, we can minimize the cost of synchronization and thread launching. So yes, it is part OpenP parallelized over mesh blocks.
I see. So basically, if your mesh block resolution is higher than your OpenMP parallelization is better.
It depends on architectures because anyway,
Like you also need to synchronize. Okay.
yeah. So it depends on how fast the thread synchronization is, and also how good its cache and memory is. So it depends. In my experience, actually MPI is better than OpenP on Intel architectures because actually MPI doesn't have to worry about other MPI processes, so they can run completely independently, and usually so it is faster than OpenP. So people think that OpenP can be faster because thread should be lightweight than process, but it's not true. Threads have to worry about other threads, so they are slower actually. And but on the other hand, for example, on Fugaku, which is designed to use this OpenP thread, we found that yes, we can get better performance by combining OpenP threads and MPI. This is partially because Fugaku's CPU has so-called fast hardware barrier for fast thread synchronization. So it really depends on hardware architectures.
Any other questions, particularly from young people, students? Don't have to worry if we are asking a silly question. Just ask questions you may have.
Yeah.
Yes, thank you very much, Kengo, for the nice talk today. We did enjoy your excellent talk.
Yeah, sorry about the technical trouble at the beginning. So, but we talk, and especially at the time that everybody's taking vacation. So, okay.
I'm glad that many people came to my talk. So yeah, I enjoyed it a lot. So thank you.
Yeah. So, thank you. Okay. Bye bye.
All right.
Bye. Thank you very much.
See you.
See you.